So we did on Wednesday a few examples of finding the area under a graph using rectangles. If you remember, we did right-hand endpoints. We were using the square root function. We did left-hand endpoints. We did midpoints. We decided towards the end of class that midpoints were more accurate for sure, but that if you wanted to be super accurate, what you would want to do is use more rectangles. Whether you use left-hand endpoints, right-hand endpoints, midpoints, if you use more rectangles under the curve, you're going to get a more accurate answer to the exact area. So that's just a summary there. So, but what we haven't talked about is what can this mean? Like what good is it to know the area under a graph? And I don't claim this is the most important one application, but it at least gives us an illustration of what this could be used for. And we will find out shortly all of the biological applications of finding the area essentially under a curve. But one of them is if you have an expression in this case for the velocity of a car as it's braking, so it should be slowing down, and it's given by f of t. I'm going to use t now because time. T minus 5 squared, that is a parabola shifted over 5 units. The bottom of the parabola is at 5. And we're only studying the velocity of the car between 0 and 5 seconds. So you do want to graph these. And there's a good reason why. I think Professor Burke kind of alluded to it, or somebody asked a great question, and that brought up the answer of why you do want to graph these. Since I'm going to go from 0 to 5, the bottom of the parabola is, let's say it's right here. And the parabola is going to go up, but I don't have a whole lot of room, so it should look something like this. Okay, let's call this 5 because I missed with my point here. I missed. All right, so let's call this 5. This is the bottom of the parabola. Okay, the rest of it would go up over here, but we're not interested in that. So this is our function. And one of the questions that came up, she started, I think, by using right-hand endpoints and then left-hand endpoints and then midpoints. Actually, I think she started with left-hand endpoints. And what we talked about last time on Wednesday is that depending on if they ask for a problem, if you get a homework problem and it says find an overestimate or an underestimate, let's not do midpoints. While it is true that when you use the midpoint method, it could be a slight overestimate or a slight underestimate. It's just a little bit harder to tell. So if they get a question where it says find an overestimate or an underestimate, let's rule that out. That means we have to make a decision whether we're going to use left endpoints or right endpoints as our system for building our rectangles. And it actually depends on what's going on with the function. Let's first do this. I'm going between 0 and 5, and we're going to use 5 approximating rectangles. So our delta x, a would be 0 notation wise. That's the left endpoint. Your right endpoint is b. So it's going to be b minus a over n. 5 minus 0 over 5 is just 1. Okay, I made this one nice. So that just means, it kind of makes sense. If you go from 0 to 5, you're going to put 5 rectangles in there, and the width of each one is going to be 1. Oh boy, I'm not very good with my space here. That's okay. This rectangle is going to look big. Just pretend that that's width is the same as these, okay? Now, in a second, we'll have an answer to this. But if we know we're going to be using left or right-hand endpoints, and we're going for an overestimate, how do we know which one? Well, let's just consider it. If I was to use right-hand endpoints for this function, and remember the way that works is start with each subinterval between 0 and 1, the right endpoint is 1. And that would be determining the height of my rectangle that covers this interval. So that rectangle would go up here and come back like this if I did a right-hand endpoint for this first one. Now you can see that that rectangle would be underneath the curve. So that's actually going to give me an underestimate. I could do this kind of lightly, like if I did this, yeah, because that's not what we want. Same thing between 1 and 2, right? If I did pick the right number here, went up to 2 and covered that interval with a rectangle there, that's going to be under as well. So it turns out in this case, right-hand endpoints actually give us an underestimate. And it's actually left-hand endpoints that give us an overestimate. Now, there isn't a way to tell. Does anybody, if you were here on Wednesday, and I'll remind you on Wednesday, do I still have the notes there? I don't know if I do. No, I don't. But on Wednesday, we did, this is me just scratching on some paper here. The function I used was the square root function. And we actually found on Wednesday that when I used right-hand endpoints, it was an overestimate, right? So, but here, right-hand endpoints gives me an underestimate. So maybe you can see the difference. What's the difference between these two functions? What's different about this function versus the square root function that we did on Wednesday? The concavity is different. I agree with that. What else? That's true. That's a true observation. Go a derivative lower than that. Like, remember concavity had to do with the second derivative, right? Well, let's go to the first derivative. What does the first derivative tell you about a function? Whether the function is increasing or decreasing. Good. And that's actually what it comes down to. If you've got a function that's increasing, then right-hand endpoints will give you an overestimate and left-hand endpoints would give you an underestimate. And if your function is decreasing, it's the opposite. Okay. That one that she drew in class, if you went back and looked at your notes, she had part of it was increasing and part of it was decreasing. And so when she used left-hand endpoints, somebody wondered why some of the rectangles were overestimating and some of the other rectangles were underestimating. And that was why, because the function was kind of changing. So that can happen too. But here, if I want to get an overestimate, then I'm going to want to use left endpoints. So between 0 and 1, 0 is going to be determining the height of this first rectangle. Now I can make this darker. I'm going to have this rectangle. Between 1 and 2, left endpoint. 2 and 3. 3 and 4, I know this doesn't look equally width, but, and especially this one does not look the same, but we'll assume it is. Now, let's talk about what we're actually finding here. We were told that the function itself gives the velocity of the car. So I didn't give units, but let's just decide on them here. Let's say velocity is in meters per second. Those would be my units for velocity. That's the Y value. And my unit for time would be in seconds. So just take one of these rectangles. What would it mean? What is the area of one of these rectangles? Let's think units. Like if I took this rectangle here, this width right here would have units of seconds, right? That's a time difference, right? And what would the height of that rectangle be? The height of that rectangle would be measured in meters per second. And what do you get if you multiply meters per second times seconds? Because that's how you'd find the area. That gives you meters, which would actually correspond to distance. So it turns out one of the applications of finding the area under a curve, if your curve is a velocity curve, the area under the graph is actually represents the distance traveled by this car. Okay. So let's find it. So we now know we're using left-hand endpoints And to find this total area, I can't see anymore. I got to move this up. I think if you were here on Wednesday and then certainly in class, all of the rectangles have the same width. So we can factor that out. So that would be like delta t. And then I would be, to get the heights of the rectangles, I want to do the value of my function at each of these numbers starting with 0. I'd want f of 0 plus f of 1 plus f of 2 plus f of 3. And for left-hand endpoints, the last number that you're going to use that determines the height of this last rectangle is actually 4. You're not going to use the 5 for left-hand endpoints. I should say approximately, right? We're doing an approximation. The area is approximately delta t, which is 1. You can't see the equation anymore, but remember that this function, the equation of this function was, it was actually f of t is t minus 5 squared. So f of 0, if I plug in 0 for t, I get negative 5 squared is 25. F of 1 is negative 4 squared is 16. This will be 9, 4. And then when x is 4, that's just going to be 1. (25 plus 16 is 41, 50, 55. Okay, so and that's times 1. So this would be 55 meters. And so that would represent, this is an approximation, right? This is approximately how far the car traveled as it was braking. Approximately. Yeah, okay, thanks. Good question. Yeah, where do I get the 25? So I'm going to be plugging these numbers into my function, which was t minus 5 squared. So the 0, if you plug that in for t, you end up getting negative 5 squared. That's how I got the 25 and so forth. Okay, so this is just a bunch of number crunching, right? You have to understand the system, but then ultimately to answer these questions, it's a bunch of number crunching and stuff. Now, you should be able to approximate area under a curve if you're given the equation of it like this. But more often than not, I mean, and I'm thinking in the world of science, you know, nobody gives you an equation for the velocity of your car as it's braking. What usually happens in science, right, is you get a bunch of data is what you get. So a more realistic problem, and one that I would expect you would be expected to do in Dr. Burke's class, is to be able to take some data. I don't have an equation here. This is actually number 7 from the book, 5.1. And we're told that the speed, which is the same as velocity in this case, of a runner, so kind of like this one, is increasing steadily during a race. And somebody kept track of her speed at half-second intervals. So this table here goes by half seconds all the way up to 3 seconds. And this is the runner's velocity at each of those checkpoints. And what we could do with that is also get an estimate. We're going to find lower and upper estimates for the total distance traveled by the runner, which again, because this is a velocity, we have velocities, that would be the equivalent to finding the area under the curve. Now, what curve am I talking about? We don't have an equation, but what we could certainly do is imagine an equation, imagine a graph, right? You could take this data. I want to make this too big, or I won't be able to fit everything in here. Here's t, Here's my velocity at t. Oh boy. Let's call this 2.5 and let's call this 3. But couldn't you imagine these velocities as, little data points along the way? So I got to keep track of my scale here. So let's say this is 6.2, 10.8. We're told that the speed of the runner is steadily increasing, and that's actually useful because we could imagine, we don't know what's happening in between. All we have are these 6 data points for the velocity, I guess 7 if you include 0, but we don't know what happens in between. So, without them saying that, we don't know, maybe she slowed down for a second and then speeded up, right? Or something like that. But if we're told that she's steadily increasing her velocity, then we know this is an increasing function over time, which is kind of important because if we want to find a lower estimate, and we know this is an increasing function always, what kind of endpoints should we be using, left or right? Type it in the chat. We want a lower estimate. All right, good. I'm seeing a bunch of lefts here, mostly lefts here. Yeah. So if it's increasing, now what you're going to want to do, I might have to draw 2 graphs here, or maybe if I use a different color, I could do this. Let's start from the right and we'll work our way backwards. So for our first subinterval between 2.5 and 3, if I want to make a rectangle that's underneath the curve, an underestimate, then I'm going to want to use the left endpoint for this one, right? I'm going to want to make my rectangle like this. And same thing between 2 and 2.5. And the difference here, right, from the one we just did is that this is an increasing function versus the one we did before, it was a decreasing function. So your left endpoints actually give you an overestimate. And actually, since the velocity of the runner at 0 was 0, we really don't get a rectangle for that first interval. So we really just need to find the areas of these 4 rectangles. Now, it really is the same process. If I want to find the area, it really is delta t times f of, we're using left-hand endpoint, so I'd be doing f of 0 plus f of 0.5 and I'm going to stop at 2.5. That's the last rectangle's height I need. But the difference, of course, is I don't have a function to plug in 0. I just know that, maybe more accurately, instead of f of 0, I should have put v of 0, right? That's the velocity at 0. This is v of 0 and v of 0.5. These are all v's. Because we're just given those, right? There's no function to plug it into. It's just, we know the velocity at 0 was 0. We know the velocity at 0.5 was 6.2. So this is just a matter of stealing the numbers from what's given in the table. And I don't know what this works out to be, but I did a good thing and I selected an odd numbered problem. What's good about choosing an odd number problem to practice? Yes, the answers are on the back. Some of you know that's one of my sayings. Life is like an even numbered math problem. Why is life like an even numbered math problem? If you want to find the answers to life, unfortunately, it's an even numbered problem. There's no answer in the back of the book, is there? Yeah. Got to figure it out. Okay, so I was biding time here. According to the book, this comes out to be about 34.7. I know you guys can add numbers, so we can do that later. Will Chegg give you the answer to life? Oh man, I haven't tried that. Oh, I know Alexa doesn't. I forget, what does Alexa tell us? Alexa. Okay, so what would change for an upper estimate? What would you be doing for an upper estimate in this case? Exactly. You'd use a right-hand endpoint. And so the only thing that I was thinking I could maybe get away with, you can't see color too well on here. Maybe I'll just redraw just a real quick. Oh boy. So yeah, if you were going to do an overestimate, then you would want to choose right-hand endpoints because that's going to go above the curve. This one was 0.51, 1.5, 2, 2.5, 3. So now so this is, this is an underestimate. I'll put for overestimate, use right endpoints, and your area is just going to be delta t again. This time the first number you use is 0.5, and you will use 3 in this case. So this comes out to be 0.5 times, we've got these values, 6.2 plus 10.8. And according to the back of the book, that should be about 44.8. Oh, I better put units. I'm going to be, yeah, make sure, especially in your class, units are important. That would be in feet. Thanks, Daniela. Okay, so the next thing, any questions on that? In some ways, a question like this is easier, right? You don't have anything to plug into, right? You're given all the numbers for you. So it might be better if it was a quiz question like that. So as you saw, since we're going to be adding you can tell we're going to get in the business of adding a bunch of things together. That's why we're transitioning over, and we're going to talk about sigma notation, because sigma notation will, number one, give us a way to more concisely write all of, if we want to say, if we wanted to add, like, what if we had like 10 rectangles in here, right? That's a lot of things to write down. So sigma notation can shorten things up. And the other thing it can do is, with a few rules, we can actually add up the numbers a little bit easier. So let's do some examples with this. All right. So this sigma is also called a summation. And so it's a formula telling us, in this case, the first number we're going to plug in for I. This formula is going to tell us how to generate the numbers. And this tells us the first number we're going to plug in for I is 1. So if we do that, we're going to get 1 squared plus 3 times 1. I'm going to put brackets around this just to emphasize that that's what we get when I is equal to 1. Then I becomes 2. So this is called the counter. I switches to 2. And if I is 2, we get 2 squared plus 3 times 2. Three squared plus 3 times 3. And then the last one is 4 squared plus 3 times 4. Like I said, I know you can add. So in this particular problem, I'm not really so concerned about what the final answer is. What I want to use this example to do is to convince you of something. And this actually came up in class too. I kind of like actually having her class right before mine, at least for me, because I can kind of follow along and see where the questions are, the confusions arising. How many people agree the order that you add numbers does not matter, right? It does not matter how you add numbers. You can add them from left to right, or you can add, some of these here and then some there and then some here. You can add however you want to. So isn't it true then that if I decided to, I could take all of these squares, I could go 1 squared plus 2 squared plus 3 squared plus 4 squared. I could take those if I want to. And then I could take all of the 3 times 1 plus 3 times 2 plus 3 times 3 plus 3 times 4. And furthermore, I'm going to leave these the same. For these last 4 terms here, since they're all multiplied by 3, I could factor out the 3, and then it would just leave me with 1 plus 2 plus 3 plus 4. All of that I did to show you and to convince you that if I think about this original summation, I squared plus 3 times I, that could be written. What are all these numbers? Those are that's just I squared, right? That's 1 squared, 2 squared, 3 squared plus 4 squared. So this right here is just the summation from 1 to 4 of I squared. And this right here is 3 times the summation from 1 to 4 of just I, right? Think about it. That would give you 1 plus 2 plus 3 plus 4. Yeah, the top number tells you when to stop. So what does that tell us? One of the properties of summations is if you have 2 things added, you can split them up. And what it also tells us, if you have a constant times I, let's say, you can actually factor that constant out of the summation. Okay, so we'll say, we can break up into two separate sigmas, summations, and factor out constants, which is what happened there. And that's actually going to make our life easier. Particularly, so here's where we're headed. We're going to get there. I'm going to give you a problem before we go. If you didn't bother to do this, it would not have taken you very long to just add up these four terms. You could have done that. You would have been done already. But the idea is, what if this wasn't from 1 to 4? What if this was from 1 to 40? Right? What if this was a larger number here? Well, then it might take a little more time to do that, right? To add them up one by one. And even if I had 40 here, I mean, even this would be hard and this would be hard. So what we need are some additional formulas that are going to help us add up numbers when we have a large number of them to add up. And so one of the formulas you're going to see, I can't remember if you learned this today or not. I think you might have. I know one of them you did. She showed you I squared. But anyhow, one of the formulas, I'm going to use this example to introduce a formula to you. Say I wanted to add up the summation from 1 to 100 of I, which would be the sum starting with 1, and then I becomes 2, plus 2, I becomes 3, plus 3. Keep doing this. At some point, you're going to end up with, when I turns to 98, and then I turns to 99, and then finally, when you get to 100, you're done. This particular summation is actually kind of somewhat famous in the math world. I'm curious if anybody has heard. Usually a math teacher likes to tell the story, but has anybody heard the story of Gauss? Anybody have a math teacher tell them this particular summation is associated with Gauss? Oh, good, I get to tell the story. Yay. So the story about Gauss was, a mathematician in the, 1800s, 1700s, a long time ago, right? And like many famous mathematicians, Gauss was one of those child prodigies, right? Those kids that you all had in your math class. Well, you were probably the kids. You were probably the ones where, your math teacher would give a problem and you'd be like, I know the answer, right? I bet you were, Bella. So imagine this child prodigy in like an elementary school, right? And, as a teacher, I've certainly had my share of Gauss students. And of course, you're like amazed and impressed and everything. But there's sometimes it's like, can you give other people a chance to answer the question? Can you just be quiet for a minute, let other people think, right? So I'm imagining that's the story, how the story was set up was Gauss was so annoying. His teacher was so annoyed with him that according to the story, the teacher said, you know what, Gauss, I'm going to keep you busy for a while. Can you go over in that corner? And I want you to add up the numbers from 1 to 100. Thinking that was going to keep him busy for a while, right? Well, as you probably expect, Gauss came back in a couple of minutes and said, here's the answer, teacher. What else do you have for me? And the teacher was probably like, oh, right? But it's a kind of a funny story, but the way he added the numbers is actually a tool we're going to use to come up with a formula. So I'm curious, does anybody see, you got to think out of the box, so to speak, a clever way of adding up all of these numbers so that you could quickly determine what the sum is? In other words, do we have any Gausses in here? Oh, I think we do. I think Maya could be a little Gauss there. Yeah. Lexi, good. Yeah, I think either of your ways would work. I think what Maya's seen is if you do 1 and 99, that's 100, 2 and 98, that's 100, the 3 and the 97. You're leaving out the 100, but you could always add that in at the end. That's totally exactly along the same lines of what Gauss did. What Lexi's suggesting is that if you included the 100 and you grouped them, so what's 1 plus 100 gives me 101, right? 2 plus 99 gives me 101. 3 plus 98 gives me 101. And so if you keep grouping them like this, the question then becomes, how many groups of 101 will you have? How many pairs? If you're taking 100 numbers and you're taking 2 of them at a time, it makes sense that there's going to be 50 pairs of 101. So the sum should just be 50 times 101, which comes out to be, I think it's 50-50. Yeah, 50-50. No, 50-50. What is 50 times 101? Well, 50 times, yes, 50-50. It's 5,000 plus another 50. Yeah. Okay. So that's pretty cool, right? That's a pretty clever thing. But what it gives us a way to do is we could not only do this for 100, we could do this for any number you want. If you change this number now, I can think of a way to figure this out. So we have a formula. If you want to add the first n counting numbers, whatever number you want, if you go 1 plus 2 plus 3, all the way up to, well, eventually I'm going to go up to n. But in order to see it, I'm going to take the term before that would have been n minus 1, and the term before that would have been n minus 2. And if you do the Gauss thing, if you start grouping things, everything you pair, first and last, gives you n plus 1, n minus 1 plus 2 gives you n plus 1, 3 plus n minus 2 gives you n plus 1. So you have a bunch of n plus 1s. How many pairs of n plus 1s will you have? I'll put blank pairs of n plus 1. How many people agree it makes sense? Just like with the 100, you would have half of n, huh? Whatever n is, you're going to have half of that many. You're going to have n over 2 pairs of n plus 1. So this sum becomes n over 2 times n plus 1. So what we usually do, since it's going to get multiplied, is you just put that all together like this. And this formula ends up becoming kind of useful. I'm pretty sure Burke said that she would give you any of the formulas you need. So I don't necessarily think you need to memorize it. You should just be aware of it. This is the sum of the first n integers. I'm going to skip here because I'm looking at the clock. So for example, if you want to add the summation from 1 to 50 of 2 times I plus 3, we obviously don't want to plug in 1, 2, 3 into this whole thing and do it 50 times, right? So we're going to combine a couple of things. We're going to use our properties of summations, which we agreed we could break this up, right, if it's plus, and we can factor out constants. So what I could rewrite this as 2 times the summation from 1 to 50 of I plus the summation from 1 to 50 of just 3. That's using the properties. And then for this one right here, using this formula here, I don't need to, I mean, you can write it out again if you want to and do Gauss's trick again, but it's going to be, n here is 50. So the sum of from 1 to 50 is going to be 50 times 50 plus 1 divided by 2. 50 plus 1. And then here, this will happen too. If you get a summation, remember how summations work. You're supposed to plug in 1 for I, and then 2 for I, and then 3 for I. But if you have one where it's just a constant and there's no place to plug in I, guess what happens? When I is 1, so I'm going to put this is what's really telling you to do. When I is 1, you get 3. When I is 2, you get 3. When I is 3, you get 3. So all this really means is you're going to be adding 3 plus 3 plus 3 how many times? 50 times, right? That's all that means. So if you add 3 plus 3 plus 3 50 times, that sum is just going to be 3 times 50. It's going to be 150. Yeah. I know you guys can work that out, so I'm going to just leave it like that, because I wanted to get to a couple more examples that you might find useful for your homework. Any questions on that, though? For the homework that you're working on your WebWorks, another useful formula, this is the one she introduced in class, so I'm just going to write it down. She already spent some time on it. And there's no clever Gauss way of adding numbers here to get this formula, but if you add the sum of the first n perfect squares, so this would be like 1 squared plus 2 squared plus 3 squared, all the way up to some random number n squared. That's a little bit harder. You can't do the grouping thing like Gauss did. But there's a way to show that the sum of this will be n times n plus 1 times 2n plus 1, all divided by 6. This one, I think I can quote her, said she will give you this, so you don't have to memorize it if it shows up on a test or a quiz. I didn't see this in the homework or in Professor Berg's class, but it is in our book. If you had to add up the sum of the first perfect cubes, 1 cubed plus 2 cubed plus 3 cubed, all the way up to some number cubed, this one's actually easy to remember. It's kind of interesting, actually. It turns out that if you want to add the first n perfect cubes, here's the formula. n plus 1 over 2. What does that look like? That's like just the sum of I, right? Squared. It turns out that the formula for the sum of the first n perfect cubes is just the same formula for just I, and then you just square the answer. So kind of interesting. I'm running short on time, so let me get to this last one. I think this is the one you want to see. Sorry, there we go. So I like the problems better when they actually give you, it's just, I don't know, a little more interesting, like an actual number, like from 1 to 20 or 1 to 50 or 1 to 100. But you have one on your homework where it's just asking for the sum from 1 to some random number. Okay, so let's say my formula, oh, and there's a reason for this. Our book uses I as the counter. The old textbook we used to use for the 17 series used K as their counter. And the WebWorks is, she's using problems from the old textbook to generate the WebWorks homework. So it's going to say K, but just know it's the same thing. So all these same formulas apply. They're using K. What you would want to do here, though, is don't, first of all, don't just start plugging in. You want to take advantage of these formulas, and the way to take advantage of them would be to FOIL this out. Because that's going to be K squared minus 9. And then split this up using, that's one of our properties, minus the summation. You can take like the minus out. And then this formula we had, right? That's the same as I squared. This is going to be n times n plus 1, 2n plus 1 all over 6. And then again, remember that if you just have a constant like this, it's just telling you to add 9 plus 9 plus 9, in this case, n times. So what would 9 plus 9 plus 9 n times be? It's just going to be 9n, yeah. And I wouldn't try to do anything with this. Just leave it like that and type it in. All right, I see I'm pretty much 1 o'clock here, so I better stop. I'll stop the recording anyhow.